Creationism. I like this Kitcher piece quite a bit. And since I couldn't really anticipate what is going to engender the most discussion, I didn't create the 1-minute argument question yet. I mean, actually, I did create it. I just didn't populate it with a question. So there will be a question today. I like the way that the semester's going. I like the quality of the contributions so far. So today is Kitcher. Then we finish this section. We have no presenter for the next class, but we'll talk, at least for a day, on some of the important differences between the physical sciences versus the social sciences. And then we'll shift our attention to one of the really important topics of this course, which is explanation versus law. Jonathan's going to be doing the presentation on Hempel, and then you can see what else we're doing. So the semester's rapidly moving along. Let me get out of this. Go to Kitcher, all right, so lecture 10, Kitcher, believing where we cannot prove. Here's an image of the guy. He's British, born 1947, still alive, still very, very, very active in publishing. Publishes in philosophy of science, as well as philosophy of biology and philosophy of mathematics and even bioethics. I mean, he writes in quite a bit of a number of different areas. I note that he got his PhD from Princeton because he ended up working with two of the big figures for our class. One's Hempel, who we'll get to when we're talking about the deductive nomenological model of scientific explanation, as well as Kuhn, who's going to occupy us at the end of the semester. He's been teaching at Columbia for a long time. He coined the phrase good science. He did a lot of stuff. And this comes out at the end of this particular piece that we have today, which comes from this first of the two books that I note on the slide, Abusing Science, The Case Against Creationism, from 1982. All right, so that's where our piece comes from. He has written on a number of other topics. So here is Kitcher. Now let's get out of this and get to our presentation. Go to, well, which one is it? There we go. All right, Martin, I'll turn it over to you.
Kitcher, believing where we cannot prove. I've read the purpose of this to demonstrate that while virtually all science is an exercise in believing where we cannot prove, science is not embraced by faith alone.
I think you're spot on there in identifying what the purpose is. We could add some more stuff to it, but I like the fact that this actually corresponds to what he says.
Yep. And
I want to draw your attention to this. If you take a look at the structure of the essay, we've got the title, you got his name, and then you've got section 1, opening moves. Flip the page over, and at the end of section 1, he says, and this is where Martin got this, we should reject the creationist gambit. Eminent scientists notwithstanding, science is not a body of demonstrated truths. Virtually all of science is an exercise in believing where we cannot prove. Yet, scientific conclusions are not embraced by faith alone. And we don't have to worry about Tennyson here because I'm not going to read that quote. I'm mentioning this because notice that right below that you've got section 2, inconclusive evidence, and so on. Well, in the essays you're going to be writing for me, maybe for the first time, you're going to be breaking your essay explicitly into different numbered sections. And I'm looking for very specific kinds of information into each of these different sections. And many of the pieces you're going to be reading this semester are broken up exactly the same way. What he doesn't do is explicitly state, well, my purpose for this essay is to show that such and such, which I'm requiring of you. But nevertheless, the kind of essay that you're going to be writing for me in this course is exactly the kind of essay that you see here. Well, it's going to be a lot shorter than the essay you see here, but it's going to be structured in a very similar kind of way. All right, so I think you're right about the purpose. Let's turn our attention. We can skip the Tennyson as you did.
Yeah.
Let's go to your section 1.
Okay, opening moves, creationism versus evolution. If faith is believing where we cannot prove, and evolutionists cannot really prove that new kinds emerge, considering the ages of time required, then evolution is more a science faith than a fact.
That's the charge that proponents of creationism. And then this piece is sort of dated, right? 1982. It was still at a time when many school boards were trying to get creationism taught as an alternative to the theory of evolution in science. All of those were struck down, right? So what creationists did was they tried to put more scientific trappings on their principles and methodologies as such. And it goes from being creationism to intelligent design. That is, they go away from explicit references to the Bible and Genesis and whatnot as part of their explanatory framework and focus on an intelligent designer without naming God as the intelligent designer. And they strip the theory of its commitment to specific passages in the Bible. They'll still get struck down, but we live in a state that has succeeded in some sense in getting that kind of curriculum included as an alternative in science courses, which should be alarming to you. So even though creationism doesn't exist in the way that it did back in 1982, way back then, right? It still lingers. It just goes by a slightly different name. So this is very much a topical issue, even though we're well past 1982.
I didn't put it in the outline, but one of my main reasons for selecting this piece was that it focuses right in on the main reason for taking this course. I have a number of relatives and old friends from high school that are creationists. I mean, they trap it up as creation science or intelligent design, but the arguments have generally been the same thing.
Exactly right.
And I have to, it's an ongoing thing.
Well, I've certainly had these debates many times over the years, even recently. And there again, these
This is a live issue.
It's very much a live issue. It's very much occupying the attention of various courts around the country. So.
I mean, right now it might not concern most of you, but like I've got a grandchild, so I don't want to see this being bandied about as science.
Well, and we've got some really good topics that come out of this particular piece. So
let's go.
Let's go.
So if evolution is conjecture or faith, then scientific creationism deserves at least equal time. Quote from page 77. Evolution is not part of science because, as evolutionary biologists themselves concede, science demands proof, and as other biologists point out, proof is not forthcoming.
I can't see that quote.
It is
Into the second to last paragraph.
yeah, second to last paragraph.
Well, because I've got a different edition, right? So my pages are slightly
Oh,
different.
okay. It's the paragraph starts with "in their attempt to show that evolution is
All right.
not science."
In the paragraph above that, in the middle of it, he says, or he characterizes the way that opponents of evolution typically phrase part of the criticism, and that's that evolution, he said, is just a theory. And I can't count the amount of times I've heard something like that. And I've already identified to you that that's an issue for us in this class, because only someone who really doesn't know what a theory is would say such a thing. That is, well, a theory, that means it's unproven. And if it's not proven, then we ought to make room for alternative theories, is part of the idea. So we're going to be dealing explicitly with what a theory is. And some of that's going to come out today, but we're going to be dealing with it more as the semester goes on. So,
Like fire-bent creationists then argue that anti-religious educators deform children's mind with a doctrine, evolution, taken on faith, not science.
right. So we're just setting the stage here.
Yeah. So number 2, why is science fallible? Inconclusive evidence section. Page 78. Is there really anything of which we are so certain that later evidence could not give us reason to change our minds?
Which is exactly the sentence or the question you should emphasize here. And let's pause there for a second. Is there really anything of which we are so certain that later evidence could not give us reason to change our minds? Is there anything? I mean, anything that we would claim to know or understand about the world that we couldn't discover evidence at some point in the future that would show that what we believed was wrong?
You have to be pretty stubborn to things that are true by
That is-
definition.
I mean, that was Descartes' question in the Meditations.
It's a what?
That was similar to Descartes' question in the Meditations, looking for the one thing that he can be certain of.
No. Descartes in the Meditations is using doubt methodologically in order to discover some one thing that's impossible to doubt, right? the issue here is there any, maybe we could apply, in fact, what does Descartes discover as he uses this method?
I think they're far
That
ahead.
is, that is doubting, affirming, believing, willing, all require some subject, something that's thinking, doubting, willing, and affirming, and so on. So long as he's having those kinds of thoughts, he must exist. He doesn't then know what he is then, so he explores that. But I think we should probably bracket that particular case, right? Because I think it's sort of odd to even put this in that particular context. That is there anything we could discover later that would show that we're wrong about our own existence?
Well, the perceptions were in existence, but not the fact that they exist.
Yeah, I mean, it's hard to imagine. Maybe at some point in the future we'll be able to download someone's consciousness, right, and upload it into a computer, a kind of simulation, such that you end up, in some sense, existing, but it turns out that you don't have a body, right? That is, from the standpoint of what you're experiencing, if you were a brain in a vat, the world would still appear the same way. Is there anything that you could experience that would show that you're not a brain in a vat? And the answer is, well, no. But these are sort of philosophy of mind kind of issues, not so much philosophy of science issues. So let's go back to the issue here. There are lots of things that we would now claim to know or believe, certainly be justified in believing about the world. Is there anything that we would claim to know or believe that's so certain that there isn't anything that we could discover later on that would show that we were mistaken?
Do you mean something about the world?
Yes. And for Quine and for other conventionalists, it's not just about the world. The truths of logic are just as revisable as are the empirical truths based on observation and test, right? But he'll answer the question at the top of the next paragraph. So go ahead and state that, Martin.
Yeah, fallibility is the hallmark of science.
Right. Complete certainty can best seen as an ideal toward which we strive, and that is rarely, if ever, attained. What do you think about that? Do you think he's right? Or do you think he's wrong? Do you think, no, science gives us certainties all the time?
Well, that's probably the problem sometimes, is they're often presented, maybe not by scientists, although occasionally by the scientists themselves, but it's often presented as, wow, it's a new truth.
Presented by whom?
Yeah, that's what I said, often by non-scientists, by commentators, by, whoever's got an axe to grind for that particular new fact. Occasionally, though, and Kitcher cites a few.
He does.
Occasionally, a scientist will be guilty of doing the same thing.
And creationists or proponents of intelligent design are fond of appealing to those kind of scientists as a part of their attempt to bolster their argument. Well, look, even this scientist says that it's not proven, therefore it's not proven. Do you have something you want to say?
Oh yeah, I was just going to say, I think that fallibility in the hallmark of science, I think that's something that people don't necessarily like sometimes, like even recently, like when Pluto stopped being a planet. The general public, for whatever reason, kind of didn't like that because, as far as they knew growing up, this was a fact.
Right.
Scientists told us this was true, and now it's being revised.
Yeah, I like that page on Facebook. That's whatever it is. That.
When I was your age, Pluto was still
Yeah, I mean, I've liked that page, right? But it didn't. The object itself, referred to as Pluto, didn't itself change. What changed such that at one time it was a planet and now it's not?
Definition.
Not the definition, but the identity conditions that must be met in order for something to be a planet, right? So it turns out the conditions have to do with the shape of it, being in an elliptical kind of orbit around the sun kind of thing, as opposed to, what's that?
In the same plane as the other.
Yeah, I don't remember the exact conditions, but they changed the conditions such that it ends up being demoted. And it's specific, it's not, there's another name for it. It's like a dwarf planet or something. I mean, it's not a full-fledged planet. The point is, one of the hallmarks of empiricism now, in light of work by people like Kitcher and other folks in philosophy of language and philosophy of science, is that, and this comes out explicitly in his piece today when he talks about the Duhem thesis, that there isn't anything that we now hold to be true that we can't give up in face of better evidence to the contrary. that we shouldn't be troubled by that. We shouldn't be troubled by the fact that there are things, very likely things, that we now believe to be true, things about which we're almost certain, about which we're mistaken, and future evidence will show us that that's the case. So part of the issue here, I just wanted to pause and mention this, is that you shouldn't hold science to a standard it's not possible to attain, because certainty about things that we discover about the world is impossible, and it's impossible for a reason, namely the problem of induction. That no amount of evidence based on the past will ever guarantee that the future is going to unfold that way. Now we can have 99% certainty, but that's pretty strong, but it's never going to be guaranteed. So don't seek guarantees where guarantees are not possible. Aristotle says pretty much the same thing in the Nicomachean Ethics for a different reason. But it's not reasonable to seek guarantees about something that can't possibly be guaranteed, and by guarantee I mean certainties. So, interesting discussion. We've had this before. We're going to talk about it more. But I think he's absolutely right. Complete certainty is best seen as an ideal toward which we strive and is rarely, if ever, attained. And that, as Martin said, fallibility is the hallmark of science. That's not saying something bad about science. I mean, it's really the hallmark of science. So I like this thing that he says in the next paragraph. He says, the history of natural science is strewn with the corpses of intricately organized theories, each of which had in its day considerable evidence in its favor. When we look at the confident defenders of those theories, we should see anticipations of ourselves. I really like that.
Yeah.
Because, again, over the course of the semester, we're going to be looking at a lot of historical examples. And right now, as confident as we are about the truths of certain things and the certainty of certain things, we could just as easily be shown to be mistaken as a result of some future experiment or innovation in technology or whatnot. I'm not saying it's going to overturn 90% or 50% or whatever what we would now claim to know. We just have to accept the fact that fallibility is the hallmark of science, not certainty. Okay? Are we cool with that? All right, then Martin, let's move on.
Okay, yeah. Science not only aims to disclose general principles that govern the universe, but also advance claims about things that are beyond our power to observe. So, how is science possible at all? Scientists single out some things we can see and use them as clues to how nature works. Page 79, scientific theories rest on indirect arguments from the observational evidence.
Well, he's got more to say about that.
He's got more in there.
So,
Yeah.
keep going.
Yeah. Any alteration of the assumptions that a theory is based on may require change in or even discarding a theory. Once the fallibility of science is recognized, then we can move into the vast field of cases which can be believed on the basis of good but not inconclusive evidence. All theories are revisable, but not all theories are equal.
And let's pause there, because that's a really important statement. And I've made that statement here for us a couple of times already. Let's take a look at the beginning of that paragraph. He says, if we want to emphasize the fact that what scientists believe today may have to be revised in light of observations made tomorrow, then we can describe all of our science as theory. But the description should not confuse us. To concede that evolutionary biology is a theory is not to suppose that there are alternatives to it that are equally worthy of a place in our curriculum. And again, as Martin just said, all our theories are revisable, but not all theories are equal. I like that quite a bit. Then we come to the end of this section. We get to section 3 on predictive success. Okay.
Theories win support by producing claims about what can be observed. Claims that would not have seemed plausible prior to the advancement of the theory, but are in fact true when we make the appropriate observations. That's top of page 81. Observational consequences are statements inferred from generalizations about features of particular things, atoms, planets, you name it, which can then be checked and confirmed or falsified.
So the observational consequences are going to be what it is that we should observe, the event that we should observe, and the statement that captures that consequence is what we often refer to as the observation statement. Now, we've talked about all this stuff before in relation to the hypothesis. If the hypothesis is true, then it entails that we ought to observe the world being a certain way, as a part of our test, and either we do or we don't, right? He goes in a little bit more detail in terms of the logic, but what he's saying here is consistent with what it is we've been talking about. So I'll let you go forward, and then I'll stop us where we need to stop.
Okay. Theories are supported when their observational consequences are true and damaged when observational consequences are false. We say that a statement S is a valid deductive consequence of a group of statements if and only if it is impossible that all the statements in the group should be true and S should be false.
Now this,
right at the bottom of page 81.
Yeah, that's a little bit opaque, and it's rather technical. Now let's pause for a second here. What does it mean when we say that an argument's valid? Let's take a look at one of our preferred argument forms. If P then Q, not Q, therefore not P. Again, this argument form has a name. It's called modus tollens. Doesn't matter what you substitute in for P and Q, the resulting argument is guaranteed to be valid. And if you take symbolic logic, then you're going to learn a variety of methods for proving that this argument is valid. So the point is, this is a valid argument. When we say that an argument's valid, actually this is a valid argument form, a substitution of instance of this argument form would be a valid argument. But when we say that an argument's valid, what do we mean by that?
The truth of the claim falls from the truth of the evidence.
And what do we mean by that? Why is it that the truth of the claim follows from the truth of the evidence? Don't say, well, because it's valid, because that would be patently circular. So what is it?
It's impossible for the claim to be false when the evidence is true.
Exactly right. It's impossible for the claim or the conclusion to be false when the evidence is true, such that if the evidence is true, the claim must be true too. Now, if that's the case, then another way that we can flesh out validity is to say that the premises are inconsistent with the denial of the conclusion. That is, as a set of statements, every set of statements is either consistent or inconsistent. If it's consistent, then it's possible for all the statements in the set to be true at the same time. So just take a look at an example here. Here's a set of statements. P, Q, R. I'm not saying that one of these is the conclusion, right? But a set of statements is either consistent or it's inconsistent. If it's consistent, it will be possible for all the statements in the set to be true at the same time. If it's inconsistent, then it will be impossible for all the statements to be true at the same time. Now, the reason why this applies in the context of validity is because when an argument's valid as a set of statements, we can even simplify this and look at modus ponens, which is a similar kind of argument. If P then Q, P, therefore Q, all right? This is another argument form that has a name. It's called modus ponens. Now, the statements that make up the set of statements in this argument are if P then Q, P, and strictly speaking, Q. In order for an argument to be valid, the truth of the premises must be, that is, as a set of statements, it must be inconsistent. That is, the denial of the conclusion. That the premises are, that is, the truth of the premises are, I'm really trying not to be too technical about this. That is, as a set of statements, this set of statements is inconsistent. Why? Because the truth of the premises isn't consistent with the denial of the conclusion. Because if the conclusion's true, I put it another way, it's impossible for the premises to be true and for the conclusion to be false. So if it's impossible for the premises to be true and for the conclusion to be false, if the premises are true, the conclusion must be true. So to deny the conclusion when the premises are true is going to be a set of statements that's going to be inconsistent. Won't be possible. So that's what he means here. And he talks about...
He uses the George Steinbrenner example.
Yeah, well, he does, but he's talking about, in the end, what a valid deductive consequence is. And we've already covered that already when we're talking about what the scientific method is, the difference between the positive case and the negative case. But basically, you need to take a look. We've been oversimplifying things like this, right? This is a gross oversimplification. As we're testing a hypothesis, we've done it this way. If our hypothesis is true, then we ought to observe the world being a certain way. We test it. When it doesn't happen, when we don't observe what we ought to observe if our hypothesis is true, then deductively we know that our hypothesis is false, right? This is just straightforward application of modus tollens. And for reasons that Popper's talked about, we know that that's got to be the case, right? The problem is, it's, as we've already talked about, it's never the hypothesis itself, right? It's going to be the hypothesis along with certain auxiliary assumptions. And not just auxiliary assumptions, theories. Theories are going to be composed of laws and other assumptions. So it's going to be a whole bunch of statements that together will entail what it is that we ought to observe. So when we don't observe it, this isn't proper notation, that there's going to be a whole set of statements here in H, right? So when we don't observe what we ought to observe, we know that something in that set is going to be wrong. So we need to talk about it in this way, because he ends up for the first time talking about naive falsification, as if we can, as a result of a negative test, know conclusively that it's our hypothesis, when it's never going to be our hypothesis. It's going to always be our hypothesis, some other set of auxiliary assumptions we're going to have to then test. Right? We know we've got to give up something, we just don't know what it is. So, thus, a few paragraphs later, S is a deductively valid consequence of a group of statements if and only if there was absolutely no possibility that all the statements in the group should be true and for S to be false. And that's just what it means for an argument to be valid. So think of valid deductive consequence as the conclusion of a little sort of mini valid argument, such that if everything that we're assuming is true, then it must be the case that we ought to observe this. Now, does this make sense to you? We talked about the logic of testing. We're going to be talking about logic of explanation. We've emphasized the importance of the falsifiability as opposed to verifiability, because verifiability doesn't conclusively tell you anything. Falsifiability does. So I don't think he's really saying anything different than we've already talked about. He's just using a slightly different concept. He's spreading it out a bit. But we've already spoken about this as a result of our test, our hypothesis, and a certain set of auxiliary assumptions that together entail that we ought to observe this. This by itself isn't a valid argument for him, but it's going to be, I mean, we just make it more complicated, but we don't need to do that. When we don't observe it, then we know that something's wrong, H and our set of auxiliary assumptions. That is, to deny that both of them are true means that one are, as this is logically equivalent to not H or not this. And since we're using this A within this set, there's really a whole bunch of other statements there. Okay, we've talked about this in a couple different places in the semester. Does this make sense to you? All right. It should. So he mentions Popper explicitly. So
right, yeah, basically, the observational consequences of theory must be statements whose truth or falsity can be confirmed by direct observation, and which would then allow us to use Popper's concept of falsifiability.
He says this means that theories can be conclusively falsified through the discovery that they have false observational consequences. And he mentions Popper explicitly by name. So nothing.
Good scientific theory should not be false. Rather, it must have observational consequences that would reveal the theory as mistaken if the experiments give the wrong results.
Right.
And on page 83. And then we get into, his middle section here, predictive failure, where he once again is talking about the creationists. Creationists advance three types of predictive failures in evolutionary theory. The theory makes no predictions and is therefore unverifiable. The theory makes false predictions and is therefore falsified. The theory does not make the kinds of predictions it ought to make. Its predictions have no bearing on the theory. Of course, you can note that pieces 1 and 2 are contradictory.
Yeah, keep going.
Creationists dismiss as irrelevant any laboratory evidence produced by evolutionary theorists, thus demanding a standard of evidence above other science.
And I like the way that Kitcher puts it here, in that paragraph. He says, the standards of evidence to be applied to evolutionary biology have suddenly been raised. In this area of inquiry, it is not sufficient that the theory yield observational consequences whose truth or falsity can be decided in the laboratory. Creationists demand special kinds of predictions and will dismiss as irrelevant any laboratory evidence that evolutionary theorists produce. And that is, in this way, they try to defend it.
Their point number 3 on my list, theory does not make the kind of predictions it ought to make.
Now, what do you think about that as a practice? Let's say, of elevating the standards such that, well, that's a kind of a negative test, or it's whatever, but it's just not the right kind. Can anyone think of an example of this outside the context of science?
Courtroom evidence?
What's that?
Courtroom evidence?
In what way would that be an example?
Well, I mean, not that it's happened, but you could increase the standards for evidence to beyond what is reasonable for, you could say, well, if you've got a murder in a room, the moment that anybody goes in to check on the body, everything is contaminated, now we can't use any of this evidence in court because it just unreasonable standards, because somebody has to go in and collect the evidence, they've already tampered with it, it's ruined.
Yeah, well, the job of the attorneys is to plant some doubt, some reasonable doubt, because the standard for trials is beyond reasonable doubt.
Yeah.
Right? Not any doubt. That is, the standard isn't beyond any doubt, it's beyond reasonable doubt. So I would say that in scientific sense, that the standard is actually a little lower in court cases than it is in science. What I wanted you guys to consider is, what do you think about this? You're arguing with someone, you're a proponent of one view, they're a proponent of another view, and you both have the same standards applied to the view that you're maintaining, but you don't accept any evidence to the contrary. And not just are you not accepting any evidence to the contrary, you elevate what ends up counting as evidence against your view, such that it's impossible to falsify. Yeah, well, it's not just you're moving the goalpost, and I think that much is the case. There's a sense in which you're begging the question. If you don't admit of any evidence to the contrary, then if there's nothing any proponent of evolutionary biology could present as evidence against intelligent design or creationism, then they're simply begging the question. And from a logical standpoint, that's bad. When you assume the truth of the very thing that's at issue, or what you're trying to claim, and you don't accept of any evidence to the contrary, then it's simply circular reasoning. It's begging the question, and that's always bad. So when you don't allow any evidence to falsify your theory through either the addition of ad hoc hypotheses, which is bad, right? You don't allow it to be falsified or to be revised, or you just don't accept any evidence to the contrary, then you're simply assuming that it's true, but you're not showing that it's true, and that's also bad from a logical standpoint. So I think he's right, descriptively, that they've sort of raised the bar, and in terms of the standards of good reasoning, that's bad. So I like the way he puts it again. The standards of evidence to be applied to evolutionary biology have suddenly been raised, and that's not good. So the next paragraph, he says, oddly enough, however, the most popular supplement to the charge that evolutionary biology is unfalsifiable is a determined effort to falsify it. Creationists cannot resist arguing that the theory is actually falsified. So which is it? Either it's unfalsifiable or it's falsified. It can't be both.
And as he points out, you'd think they would trumpet the results if they had sound falsifiability evidence.
But remember, there's a difference between creationism and intelligent design. I mean, creationism is predicated on using the Bible as a part of the explanatory framework. Intelligent design, they can't do that. I mean, they can't simply ignore evidence to falsify. I mean, they can't do that. But it is sort of odd that they're claiming on the one hand that it's unfalsifiable, like evolutionary biologists say of creationism, and that it's falsified, which is what evolutionary biologists would say of creationism as well. So they're trying to use the same arguments that evolutionary biologists use against creationists against evolutionary biology. They're just not doing consistently.
Yeah.
Okay.
And there's a big table on page 86 of, all kinds of examples that Morris makes showing where the evolution model and the creation model are, where the creation model wins out. I'm iffy about some of these. I went through them and I didn't quite see what was being gotten at on some of them.
Well, let's go through a few of these. So take a look at the category, then on the evolutionary model side, then on the creation model side. So nature of natural laws, the structure of natural laws. In evolution, they're constantly changing, so they're settling, the view with. And the other is that they're invariable. What do you think? Is it fair to say of proponents of evolutionary theory that they view scientific laws as constantly changing? I don't know anyone who does that, right? Which means that they're guilty of what?
Strong.
Yeah, and that's always bad. I mean, you can't misrepresent your opponent's position, attack the misrepresented version, and then think that somehow you've undermined your opponent's actual position. That's what straw man is. Whereas in the creation model, laws are invariable. They don't change. The galactic universe, galaxies are changing in the evolutionary model, but they're constant in the creation model. The structure of the stars are changing into other shapes. Stars are unchanged. The other heavenly bodies are building up, whereas they're breaking down. I like a couple of these other ones. Types of rocks are going to be different in different ages in the evolutionary model, whereas they're going to be similar in all ages. The appearance of life emerging from non-life versus life only from life, and so on. As you went through this list, were you troubled by any of these?
Well, I was troubled by the statement that basically each of what it says about Morris' table, each of these predictions can be deduced from evolutionary theory only if the theory is extended by adding extra assumptions. Morris saddles evolutionary theory with faulty additional claims. These are the source of the false predictions. So I'm guessing that the faulty additional claims are all these things about heavenly bodies and things that fit into astronomy that don't have anything to do with evolution.
No, it's sort of the other way around. What he's charging is that evolutionary biologists, in order to preserve their theory from being falsified, add supplemental auxiliary assumptions, that is, these ad hoc hypotheses, in order to immunize it from being falsified. Yeah.
As for specific examples, I didn't like that he characterized the evolutionary model saying that mutations in organisms are always beneficial. But it doesn't seem like they are. Some mutations are irrelevant to the benefit of the organism.
Right, they're not, mutations are just mutations. They're neither beneficial in evolutionary theory nor harmful, except in their relationship to the fitness of the species to survive and reproduce.
In fact, let's pause there and talk about evolution for just a second. People tend to think of the theory of evolution as committing us to the notion that there's this gradual sort of incremental sort of improvements to the species. Is that what evolution is?
No.
Nothing like it. It's what?
Becoming more suitable to the environment.
No. It's that those organisms better suited to their environment are the ones that are going to survive. It's selection and adaptation, right? And this. What's the mechanism that allows for that?
It's functional.
Well, it's natural. That's the argument for natural selection.
That's what natural selection is. And how is it that we end up with differences in species? This is another big part of evolutionary theory. What is it that happens?
Mutation.
That is random genetic mutation. Ends up giving some members of the species a different trait. And as pressures in the environment occur, they can be climate pressures, they can be environmental pressures, which I suppose would be included.
Separation of one species by a physical barrier.
What ends up happening is that you end up with these changes in the species over the course of the life of the species, right? Hold on a second. So evolution doesn't commit you to sort of gradual, that is mutations that sort of incrementally improve the species so that it ends up being better or more fit. Rather, mutation occurs. And as changes occur in the environment, the species that's better adapted to the environment is the one that's going to survive. That's all the theory of evolution is. So what opponents are saying here in this context is that rather than allowing the theory to be falsified, they keep adding stuff to it in order to immunize it, in the same way that you want to hold on to your theory. You're stubbornly clinging to it in the face of evidence to the contrary. You can do that, and as Quine says, I mean, there isn't anything that can be that's immune from revision. I mean, anything can be held true come what may if you make drastic enough changes elsewhere in your system. But generally speaking, that's bad to do that. I mean, to not let your theory go in the face of, evidence to the contrary. So, what do you want to say, Adam?
Well, all of this deals with evolution by natural selection. They don't even address Gould's periodic evolution or any, and they'll bring up the fact that they debate within scientific communities. At least in the 70s, there was still a fairly heavy debate between Gould and other scientists about periodic evolution versus natural selection. And they'll say, well, there's a debate and they don't know anything, but they won't talk about any of the other. They put up a straw man and argue against only one of the proposed ideas, one of the proposed mechanisms. I'm sorry.
And there may be other mechanisms,
Yeah.
right? But the idea is that no change is occurring as a result of some intelligent designer. What creationists are committed to is that you can only get life from life. So that presupposes the existence of some living thing from which life emerged.
Mm-hmm.
Yeah.
What is meant by other heavenly bodies building up and breaking down? What does that refer to?
I do not understand that.
Well, stars, for instance.
We mentioned stars as specifically structures of stars.
Nebula.
Maybe nebula or something.
Yeah, I mean, that would qualify.
But what does that mean, building up? Like, how does that account? What does he mean by the evolutionary account says that the other heavenly bodies build up?
So think about what happens at a black hole. You've got, that is, as galaxies collide, say as a result of some big black hole, you're going to have explosions of stars and all this matter that ends up, there's a sense in which I don't think a great deal hinges on it. I mean, is there some particular heavenly body that you're troubled
No,
about?
not at all. I didn't know what a heavenly body meant. I didn't know what another heavenly body was. I didn't know what it meant by that the evolutionary model accounts for it building up and the creation model accounts for it breaking down. I didn't understand that.
Yeah, I don't think a great deal hinges on it. So I didn't focus on it myself. I wouldn't be that concerned. All right, Martin, let's keep going.
Yeah, well, as we head into naive falsification, right at the bottom of the page, to make a serious assessment of these broad creationist charges, we must begin by asking some basic methodological questions. We cannot decide whether evolutionary biologists are guilty of trying to save their theory by using ad hoc assumptions, unless we have some way of deciding when a proposal is ad hoc. Similarly, we cannot make a reasoned response to the charge that laboratory experiments are irrelevant, or to the fundamental objection that evolutionary theory is unfalsifiable, unless we have a firmer grasp on the relation between theory and evidence. And that heads us into naive falsification. If the apple falls from the tree but does not strike Newton, it does not need to falsify the laws of gravity and motion. We only have to assume that some other force was at work, and now the laws of gravity and motion are unfalsifiable. I was paraphrasing basically his second paragraph.
Yeah, I think that's a fair paraphrase. The idea is stated a few paragraphs before that is on the traditional view of theory, textbook cases of scientific theories turn out to be unfalsifiable. And that's true, because we don't allow certain evidence to count as negative evidence in falsifying the theory. For instance, why is that case with Newton and the apple a case that wouldn't undermine Newton's law?
Well, that's what he goes on to explain in the whole naive falsification, is that Newton's laws basically allow you to calculate how something is going to fall. In other words, if you use everything in there, you know the direction, the motion, the forces acting on it, then you can calculate.
I think calculate's probably the right word, but
Right.
a better word in this context is going to be predict.
Yeah.
That is, you're going to be able to predict what you ought to observe.
Right.
Right? And then you don't observe it.
Right. If you just take a piece of Newton's law, if you just take the way gravity is supposed to work and the object on the object that's falling,
Right.
then if the object, if something else can make the object not hit where it's supposed to, then you can say, oh, it can't be, it can't be falsifiable. But
Right. Suppose we all.
the laws are more than that.
Yes, right. Now that's one of the big take-home messages from
Yeah.
this particular piece. Suppose we all get suited up, board some super plane in the future that allows us to experience space travel, right? I mean, there are planes like that right now. I mean, they have modified C-130s that allow folks to experience weightlessness, like the crew of, was it Apollo 13 with Tom Hanks, that movie, right? I've seen footage of, lots of people doing this. In fact, there's this one particular plane where scientists from all over the world sort of jockey for position on the plane, and essentially the plane goes up and then it sort of free falls. And during those intervals, everyone on the plane is weightless, and they conduct different experiments and whatnot. We could do that, right? We don't have to wait 100 years for us to be able to go to some space station.
$100,000 to go next year up in the
Richard, what's his name?
Yeah,
Was it Branson or Elon
I think it's
Musk?
Branson.
Musk.
Yeah, whatever.
did it.
The point is, if we go up on the space station or in that plane during that period when everyone's experiencing weightlessness and we let go of the apple, have we disproven Newton's theory? I mean, would we allow, that is, normally, all things being equal, ceteris paribus, when I release an object, it falls to the ground, and that's a valid observational consequence of Newton's theory. Agreed?
Yeah.
All right, so we predict what would happen when I let it go. We board the plane. It's in that period when we're all experiencing weightlessness. I let go of the apple, and it doesn't fall. Have we disproven?
It is falling, because it's falling relative to the Earth, not falling relative to your perception.
We're talking about what you're observing.
Yeah, observed result.
Yeah.
So it's a valid observational consequence of the theory. Would we allow the fact that that apple isn't falling to count as evidence against Newton's theory?
No.
No.
Why?
Because Newton's theory is a sum of more parts than just how the apple falls.
And that's an important point, right? So it's not just the law that allows us to make the prediction, and it's going to be a set of other statements as well. But this is related to the point that, again, on the traditional view of theories, textbook cases of scientific theories turn out to be unfalsifiable. I mean, there's a sense in which, not just in these atypical situations like during those rare occasions when you could experience weightlessness, there are other occasions when Newton's laws don't apply. So it turns out, this is going to be a bigger issue for us. We have a piece called, by Nancy Cartwright, "The Truth Doesn't Explain Very Much." Because it turns out, strictly speaking, that most laws in science are false. But we still use them as a part of the explanatory framework in order to explain what's happened in the past and to make predictions. So the falsifiability criterion adopted by Popper, which I shall call the naive falsificationist criterion, is hopelessly flawed, he says. Now, do you think he's got Popper right here? Or is he just abstracting from Popper?
I think he's got Popper right, but at the same time, he's really going to end up using Popper, because by breaking everything down into bits that can all be really tested and falsified or not, he's going to end up using Popper.
And he says on 87, I might note that Popper is aware of this problem and has suggestions of his own as to how it should be overcome.
Right.
Yeah, absolutely right. I don't think he's really creating a straw man. We'll say T for theory. If theory, then what it is we ought to observe. We don't observe it, therefore we know that our theory is wrong. The problem is theories aren't single statements or a single law, but it's going to be a collection of statements and laws that together entail certain observational consequences. So I like what he says below that first characterization of naive falsificationists. On their own, individual scientific laws or a small groups of scientific laws are often identified as theories do not have observational consequences. The crucial point about theories this crucial point about theories was first discovered by the great historian and philosopher of science, Pierre Duhem. Duhem saw clearly that individual scientific claims do not and cannot confront the evidence one by one. Rather, in his picturesque phrase, hypotheses are tested in bundles. Well, this particular view ends up being modified slightly by Quine when Quine says, this is what now referred to as the Quine-Duhem thesis, that any statement can be held true come what may if we make drastic enough changes anywhere elsewhere in our system. That we cannot confirm or infirm our statements about the world one by one, but only as a corporate body. That is, it's going to be bundles of statements that we test. We can never test a statement on its own. So we're never really testing a theory as if a theory were a single statement, is the idea. To think that would be to embrace this naive falsificationist view, that we can falsify the theory by a single disconfirming instance, by a single case where we don't end up observing what we ought to observe. And Popper himself recognizes, well, no, because as we've already characterized it when we're testing our hypothesis or our theory or whatever you want to call it, it's never it by itself. It's always going to be it and a whole bunch of other stuff. So it's naive to think that when we test things in science that this is really what's going on, that we're testing a hypothesis or the theory, above all, a theory, as if it were a single statement, when it's never going to be a single statement. I hope I'm not beating you over the head with this, but this is an important point. So we can only test, and this is what we get from Duhem and then later Quine, we can only test relatively large bundles of claims. What this means is that when our experiments go awry, they are not logically compelled to select any particular claim that is the culprit. It could be this, it could be this, it could be this, it could be this. So then we need to do a different test in order to figure out which one it is. We know something's wrong, we just don't know what it is. So far I don't think he's really said anything that conflicts with what we've talked about. But I like this point at the end of that next paragraph. He says, consistent application of naive falsificationism can show that anybody's favorite science, whether it be quantum mechanics, molecular biology, or whatever, is not science. Of course, what this shows is that the naive falsificationist criterion is a very poor test of genuine science. Yes. To be fair, this point can cut both ways. Scientists who charge that scientific creationism is unfalsifiable are not insulting the theory as much as they think. All right, making good time. Go ahead.
You want me to go ahead with successful science?
Yeah, let's do that.
We beat naive falsification up a bit. Successful science. In spite of the problem with naive falsification, it is still desirable for science to be able to fail in order to succeed. He shows the example of the problem of the orbit of the planet Uranus and the discovery of Neptune, and how this example shows Newtonian gravitation to be testable and falsifiable. Faced with a problem in Newtonian gravitation model, scientists did not abandon the model. Rather, an auxiliary hypothesis was created which could be tested independently, i.e. that an additional planet occupying a calculated orbit explained Uranus's orbit. And when faced with the problem of Uranus, Newtonian physics as a whole proved to be unified. Faced with any question about motion, the Newtonian suggestion was the same. Find the forces acting from the forces and the laws of dynamics, work out the equations of motion, solve the equation. And of course, having solved that equation, they told astronomers where to look, and lo and behold, there was another planet. So we had something that was testable, because if no other planet had popped up, there would have been a problem. And one did pop up in the right place at the right time.
Keep going.
He gives 3 rules for successful theories.
And this is related to what makes science good, that is doing good science requires certain things, or certain virtues that good science exhibits that aren't present when we're doing bad science, right? So what are they?
An auxiliary hypothesis should be testable, independent of both the problem it is introduced to solve and the theory it is introduced to save. Good theories consist of one or at the most a small family of problem-solving strategies that can be applied to a wide range of problems. And 3, a theory should exhibit fecundity. It should open up new areas of research. A flourishing science is incomplete. It should raise questions and should presume that the questions can be answered by its problem-solving strategy.
Let's pause here. The paragraphs get summarized this way. I have highlighted 3 characteristics of successful science. Independent testability is achieved when it is possible to test auxiliary hypotheses independently of their particular cases for which they were introduced. Unification is a result of applying the small family of problem-solving strategies to a broad class of cases, and fecundity grows out of incompleteness when the theory opens up new and profitable lines of investigation. What do you think about these as the measure of a successful science, as doing good science? Do you think do you have any problems with the 3 that he mentions, or do you think anything's missing here? Huh?
Well,
It's not just you. I mean, I'm opening up to the class.
yeah, I know.
I don't necessarily think that fecundity is a requirement.
It's not necessarily a requirement, it's a virtue.
Yeah.
Right? So it's, all things being equal, better for a theory to open up new areas of exploration than not. Can you think of other examples where a theory is fecund? Fecund means fertile, right? It produces stuff. So can you think of other examples not mentioned in the text of this occurring?
You mean an example of a theory that's fecund but also not good necessarily? Oh, it's also not good.
Well, rather it would be good.
Oh, so you just want an example of a fecund theory?
Yeah. Because you have to think about it in the context of funding now, right? That many people say, well, we shouldn't be wasting money on conducting this particular kind of research because, well, we don't know what the application of it's going to be. That is, you can't always anticipate what the application is going to be. So, generally speaking, it's a good thing when an unexpected result occurs that opens up new lines of investigation. When a theory allows for the development of new technologies or applications in ways that we hadn't anticipated. That these are considered good things for a theory. That is, in terms of doing successful science, good science.
Quantum theory's been very...
What has that opened up? How has that been fecund?
It's opened up research avenues into the structure of atomic particles, the vibrations, and the use of such in the storage and gathering of information.
I think that's true. Actually.
Quantum computers.
Yeah, it's opened up research into the possible ways in which could have initiated what we propose as the Big Bang.
No, it's true. You know, the God particle stuff at the
Higgs boson field.
But these are more or less. Well,
Do you mean something like theory of radio waves and how that helped the invention of the radio or something like that?
well, no, that's too straightforward an
Yeah.
application in that case.
Well, there's
Yeah.
the case of childbed fever back in like the 1800s where they couldn't really figure out what was causing the deaths of all these women, but they kind of caught on to the fact that if doctors washed their hands between autopsies and births, that childbed fever went down dramatically, and kind of indirectly from there you get to germs and say like, why does this happen?
Mm-hmm.
And it kind of spreads.
And then they threw them in an insane asylum and they died.
And then what?
The guy who found that out, the German doctor who found out, they all said, no, it's not washing your hands, because back then, like, doctors were too good to wash their hands, like that was sort of like a society thing. So they said, no, it's not washing hands, you fool. And then they got rid of his tenure and they threw him in an insane asylum and they beat him to death.
Wow.
I just like that happy part of that theory.
Tesla's the reason you have cell phones. And much
Tesla? Oh. Well, the idea is that we can always come up with examples of applications of successful sort of tests or experiments in science. That's not so much the issue. It's that part of what makes evolutionary biology so important is that in fact, he ends up making this claim at the end of the piece. He says, so let's skip a little ahead since we're nearing the end. He says, Darwin is the
he
Newton.
goes through the Darwin one.
Yeah, Darwin is the Newton of biology. Evolutionary biology is not simply an area of science that has had some success at solving problems. It has unified biology and has inspired important biological disciplines. I mean, disciplines that wouldn't have existed otherwise. Holy crap, if we're talking about any one theory being productive and producing a lot, it's this one.
Yeah.
It's not just a theory in biology, it's the single unifying theory of all the biological sciences. As well as being consistent with the mechanisms we have in the findings from geology and plate tectonics. I mean, this is an important thing. So you knew that. It's just that he's writing this at a time when many people were defending the notion that creationism was an alternative theory to the theory of evolution, and that a theory is just a theory, right? Theory means it's not proven. So lots and lots of people have advanced the very kinds of criticisms that he mentions here. Unfortunately, they're still doing it today. They're just doing it in a different context, not in relation to getting creationism taught, but now it's intelligent design. Yeah.
Well, the fascinating thing is we didn't have the theory of continental drift and plate tectonics when he wrote.
Yeah, he had no idea of it.
When he
Well, that's
wrote
true. Absolutely right.
Origin of Species, and all that did was build up. We discovered that, and it lends itself to this.
But what opponents of evolution say, well, we're preserving it from being falsified. We're adding all this stuff to it that, strictly speaking, should be
But
independent.
it's not biological theory.
I agree with you. Yeah. Were you saying something? Like cut someone off. Any other thoughts about the Kitcher piece? I wish that we could spend more time. I mean, I could do it, but I think this was enough for us to explore the difference between creationism and, say, theory of evolution. We're going to hear more about evolution in a couple of the other pieces, but very often when folks teach philosophy of science, the examples all come from physics. And it's physics example after physics example after physics example. You hear lots and lots of stuff about Newton or astronomy and stuff like that. But in the latter part of the 20th century, we started going away from philosophy of science being synonymous with philosophy of physics to biology, because my goodness, there's been a lot of advances in the biological sciences and our understanding of biological systems in the 20th century, particularly in the latter part of the 20th century, and in particular the brain. These non-invasive imaging technologies have opened up whole fields of inquiry that wouldn't have been possible to exist. And the use of computers in modeling and information processing has opened up all kinds of avenues, for research and exploration of the brain in particular. The point is that I like the biology examples because I'm more interested in the biology than I am, say, physics, for instance. But we're doing philosophy of science, and philosophy of science, that is philosophy of the natural sciences. And physics is a natural science, biology is a natural science, chemistry is a natural science. As we get through the semester, we're going to see examples from a variety of different sciences. So if your preferred science isn't there, well, let me know what that is, and maybe we can come up with those examples. But at the very least, not all of our examples are going to come from physics, which I think is good. Because of the 9 hours each of you has to take in the physical sciences in order to get out of UNO, at least 3 of those have to be in the biological sciences. So I think it matters that we have at least some biology examples. All right, anything else for me? Yes.
Did you bring a yellow drink?
I did not. I brought an orange one in. I couldn't find the yellow ones. I was stuck with the orange. All right, then. I will post the Kitcher 1-minute argument, and I'll see you on Tuesday.